In the previous lecture, I had mentioned that in order to obtain uh, solutions to engineering problems like calculating pressure drop due to turbulent flow in a pipe, or for calculating skin friction drag on an object, acting on an object immersed in an external flow, we can make use of the fact that the turbulent boundary layer in such situations exhibits a universal structure. And this is what we are going to explore today. Klebanov was a researcher at NASA, published a landmark paper in 1955 where he reported measurements of the mean component of velocity as well as the fluctuations u prime, v prime, and w prime, and also u prime, v prime in a turbulent boundary layer over a flat plate with zero pressure gradient. So basically, he had measured these quantities. What was measured in the experiment was the three components of velocity and the UV, the product UV. And then the data was processed in a manner like what we said, what we discussed earlier. Reynolds averaging procedure was done to calculate the mean as well as the fluctuating components of the various components of velocity. This was a landmark work, and it brought out many interesting features regarding turbulent boundary layers, which were only hypothesized until then, but never established clearly. So let us take a look at these plots and then see what insights come out of this plot. The first point is that the variation of the mean velocity u over u infinity near the wall is much steeper than the corresponding laminar profile. So we can see that u over u infinity here, as you can see, drops very rapidly within a very small distance. For instance, it goes from about 0.5 or so, 0.6 or so, as you can see. It's about 0.6 here, and then drops to 0 within a distance y over delta, which is about approximately about 0.005. Notice that the u prime RMS over u infinity, which is a peak at y over delta of 0.005, which roughly corresponds to this point. So within a distance of y over delta 0.005, the mean velocity u bar over u infinity decreases from about 0.6 to 0, which is indeed a very steep drop. And so the wall shear stress in a turbulent boundary layer can be expected to be much higher than its counterpart in a laminar flow. That is the first important observation that we can make from this experimental data. The second important observation is the following. The mean flow in this case is two-dimensional because it is just boundary layer flow over a flat plate. So we expect only two of the two velocity components to be significantly different from zero. For instance, the axial component is actually significantly different from zero, and the y component, as we had shown in our laminar boundary layer analysis, is less than the axial component, but still non-zero. And the span-wise velocity component is expected to be zero, and so the flow is two-dimensional. But in this case, although the flow is two-dimensional, the fluctuations can be seen to be three-dimensional. In fact, u prime, v prime, w prime are all non-zero. And what is even more interesting is that the fluctuations in the span-wise direction, w prime, is actually higher than the fluctuation in the y direction, which is very interesting. It can be seen here that v prime reaches a maximum of about 0.04 and then drops down, whereas w prime goes as high as 0.65 or so before it starts to decrease. So w prime is actually considerably higher than v prime in this case. So this clearly shows that turbulent flow is highly three-dimensional in nature. Even though the mean flow may be two-dimensional, the instantaneous turbulent flow is always three-dimensional in nature. Okay. Now, the other observation that we can make is that the turbulence intensities, which means the fluctuations in all three coordinate directions, and the Reynolds stress component U prime V prime bar are non-zero across the entire boundary layer, and they decay to zero only outside the boundary layer. So you can see that U prime, V prime, and W prime are all non-zero inside the boundary layer, and as Y over delta goes beyond one, which means we are outside the boundary layer even here as you can see. So this decay to zero only outside the boundary layer y over delta of 1. So the fluctuations are considerable in the entire boundary layer and persist for perhaps a short distance outside the boundary layer in this case. This may not be true in all cases, but it is true in this particular case. The other aspect or important aspect that we can get from this plot is that the turbulence intensity seemingly increased towards the wall. So you can see that U prime increases towards the wall, W prime increases, V prime increases towards the wall, then begins to decrease. The wall, on account of the fact that it's a no-slip wall, exerts a decelerating influence or an inhibiting effect on the fluctuations. And as we get close to the wall, it can be expected to inhibit any velocity fluctuations. And this is seen clearly in the inset here. Although U prime seems to increase monotonically in this graph, a close-up view of the experimental data within a shorter distance shows that U prime increases and reaches a maximum at a y over delta about 0.01 or so, and then begins to increase because of the presence of the wall. And we see the same effect with W prime as well as V prime. So all the fluctuations go to zero right at the wall, and they reach a maximum and begin to decrease very close to the wall. So in this region, fluctuations are completely or are very small, and the flow in fact behaves as if it's a laminar flow in this case. It is steady without any fluctuations, and only the mean component is present. Same thing can be said about the U prime, V prime, the Reynolds stress component also reaches a maximum close to the wall and then decreases to zero. So that is what we have summarized here. So all the components go to zero right at the wall, but the peak values are very close to the wall. So the effect of the wall in inhibiting the fluctuations extends for a very short distance. In this case, y over delta about 0.05 or slightly higher than that. And U prime, V prime, we have not shown this in this particular graph, but U prime, V prime shows a similar trend. So these are the most important observations that can be gleaned from the experimental data. So what we can say about this in general in this particular case is that given the values that we have here, we can draw the following inferences, broad inferences. We can say that there seems to exist within the turbulent boundary layer three regions such that very close to the wall, which is y over delta less than 0.005, as we can see from here. So this is less than 0.005, less than 0.005. In this region, the fluctuations have become very small and viscous stresses seem to dominate. So that is what is mentioned here. So very close to the wall, the viscous shear stress mu du dy is very high, and the turbulent shear stress minus rho u prime v prime is negligible. Okay? It must be remembered from the previous lecture that the components of the deviated stress tensor look like this. So this is the shear stress mu dv dx plus du dy. So in a boundary layer, mu du dy, the mean velocity, is the component that we are talking about. And notice that its counterpart that arises due to turbulence is minus rho u prime v prime. So this is the viscous shear stress that we saw inside the boundary layer. And this is the turbulent shear stress that is also seen inside the boundary layer. So this is what we are talking about here. So we can say that very close to the wall, the turbulent shear stress is negligible, but the viscous shear stress is very large because of the huge gradient in the mean axial velocity. And slightly away from the wall, in the region between 0.005 and 0.01, which is this region here, approximately 0.005 to about this region here, the the turbulent shear stress attains a maximum, increases, attains a maximum, whereas the gradients in the mean velocity profile begin to ease out. So the viscous shear stress begins to decrease, whereas the turbulent shear stress increases and reaches a maximum. So what happens in this region is that the viscous shear stress, which was very high, begins to decrease. Turbulent shear stress, which was low, begins to increase. So they become comparable in magnitude in this region. Now, beyond this region, uh, which is uh, for y over delta greater than 0.01, the viscous shear stress becomes negligible while the turbulent shear stress dominates. Okay, so in this case, the viscous shear stress becomes smaller, and the turbulent shear stress is much higher than the viscous shear stress, because obviously the gradient du dy has become very small beyond this region, and this one is still high, so this dominates, whereas this goes to zero. So we can illustrate, we can actually then illustrate this, for instance, pictorially like this. So you can see that there is an inner region, overlap region, and an outer region where the effects that we talked about are seen. Okay. In fact, Frontal, von Karman, and Milken hypothesized the existence of three such regions. So basically, we are saying here that there are three regions, and that in these three regions there is a competition between the viscous stress and the turbulent shear stress. Millikan, Frontal, and von Karman hypothesized in the 30s, 1930s itself, that there must in general be three such layers in any turbulent boundary layer, not just the one over a flat plate with zero pressure gradient, but any turbulent boundary layer. The hypothesis must consist of three regions: inner region dominated by viscous stress, outer region dominated by turbulent shear stress, and an overlap region in which the viscous and turbulent shear stress are equally important. Okay, now you must bear in mind that the experimental data presented by Klebanov was carried out or was obtained in the 1950s, mid 1950s, whereas this hypothesis was proposed 20 years before that. Okay, so the basic hypothesis, or the basic idea that was proposed, was that there must be three layers inside a turbulent boundary layer: innermost region where the fluctuations are almost absent, and the flow behaves as if it's a laminar flow. Although it's still turbulent, it behaves as if it's a laminar flow, and viscous stresses dominate in this region. Overlap region where the viscous stress comes down and the turbulent shear stress increases, so they are comparable in this region. And an outer region where the turbulent stress is much higher and the viscous stress has decayed to almost zero. So these are the three regions that are expected to exist within the turbulent boundary layer. And it certainly seems to be true. This structure certainly seems to be present in the experimental data that was presented by Klebanov, which, of course, we must bear in mind that it was only for a turbulent boundary layer over a flat plate with zero pressure gradient. So the question that we must ask next is, how does this structure change, or is it for other boundary layer type, for other boundary layer flows, or is this structure retained, present in the same form in other boundary layers, boundary layer flows? So let us look at other boundary layer flows. So here we look at u over u infinity and y over delta for a range of turbulent boundary layers, starting with flat plate, very strong favorable pressure gradient, and then adverse and mild adverse, strong adverse, very strong adverse, it's separating flow. So the range of pressure gradient here covers all possible values, starting with strong favorable to zero pressure gradient in flat plate to mild adverse and strong adverse, and then separating flow. So if this hypothesis were to be true for all the types of boundary layer flows, then we generally would expect some kind of similarity between these velocity profiles, but at first sight, it doesn't look as if these velocity profiles have anything in common, except that the variation is very steep near the wall. Apart from that, they don't seem to show anything in common. It must be recalled that when we plotted u over u infinity versus y over delta for laminar boundary layer, we saw that there was self-similarity, and the velocity profile at any axial location appears the same when plotted as u over u infinity versus y over delta. So such a kind of similarity is not obvious here at first sight. Now, after much examination of the data, von Karman suggested that the variables to use, although for a laminar boundary layer, the variables to use are the similarity variables, u over u infinity and y over delta. He said that the variables to use in case of a turbulent boundary layer are not u over u infinity and y over delta, but instead new variables labeled u plus and y plus, where u plus is defined as u over u star, and y plus is defined as y times u star over nu. This u star is called the friction velocity and is defined as the square root of the wall shear stress tau wall divided by rho. So if we replot this data, so basically we go to each one of this velocity profile, calculate the wall shear stress from the profile, and then based on the wall shear stress, we calculate the friction velocity. And using the friction velocity, we replot the data in terms of these coordinates. Then it is clear that except for the case of separating flow, all other cases collapse onto the same curve in a region that looks like this. So you can see that if it is plotted on a semi-log plot with y plus on the x-axis and u plus on the y-axis, you can see collapsing of the data in this region, which is about 35 or so to about 300, 350. So in this region, y plus lying between 35 and 350, we see that the velocity profiles of all the cases, flat plate to favorable to very strong adverse, all of them collapse onto the same curve. And this, if I use a curve for it, appears to be a straight line in semi-log coordinates. And this region is the overlap region that we mentioned earlier. So this region here is the overlap region that we mentioned. So it seems that the velocity profile in the overlap region actually is logarithmic in nature. And that is what we are saying. So the overlap region, in the overlap region, the velocity profile is logarithmic. Notice that this is the outer region, and we don't actually see any similarity in the outer region for these flows, but we see a universal structure in the overlap region for all these types of flows. By universal structure, what we mean is all of them collapse onto the same line, but there is no universal structure in the outer layer. And notice that there are no data points in the inner layer in this particular for these flows. So these are external flows under different pressure gradients, and we can summarize by saying that for this case, there is no data on the inner layer. Outer layer shows a universal structure, the logarithmic velocity profile. I'm sorry, overlap layer shows a universal structure with the logarithmic profile, and there is no universal structure in the outer layer in this case. Okay, so we can now write the velocity profile in semi-log coordinates like this. So K here is called the von Karman constant, and B is also a constant. So basically, it can be seen that 1 over kappa is the slope of this line, and B is the y-intercept of this line when plotted in semi-log coordinates like this. And the usually accepted values for these constants are kappa equal to 0.4 and B equal to 5.5 as suggested by Nukuradze. So notice that there is no data in the inner region here, and we know that inner region is the region where viscous stress dominates and the fluctuations are completely absent, so there is no turbulent shear stress, but there is no data shown here, but it is well known from other experimental data in pipe flow that in the sublayer, inner layer or viscous sublayer, the inner layer actually has many names. So earlier we referred to it as the inner layer. The inner layer has several names. It's called the inner layer or viscous sublayer in some instances. It's also called the laminar sublayer, although that is probably erroneous to call the flow laminar. But the word laminar is used to denote the fact that their fluctuations are completely absent in this part of the boundary layer. So in the laminar sublayer or viscous sublayer, it was shown through experimental data that U plus varies linearly as Y plus. And this is now well accepted for external flows as well, although this was established first in pipe flow measurements. So it is so we can summarize our finding so far by saying that for external flow, that is boundary layer flow and different uh, pressure gradients, and for different Reynolds number, the overlap layer shows a universal structure with logarithmic velocity profile, and the inner layer also shows a universal structure with a linear velocity profile, and there is no universality in the outer region in the case of external flows. Now let us turn to flow through pipes. You may be recall that our primary purpose in going through this is to come up with relatively simpler ways to calculate external skin friction drag or pressure drop through pressure drop in a pipe flow due to turbulent flow. So we have already shown that for external flows, there is a universal structure for the inner and the overlap layers. Now let us take a look at pipe flows. Now, very careful measurements were made by Nukratse and by Lindgren and others in pipe flows for values of Y plus ranging all the way from the viscous sublayer up to the outermost region. And it can be seen that for internal flows also, the turbulent boundary layer shows similar three-layer structure like before. So here is the inner layer or viscous sublayer where the velocity profile varies linearly with Y plus. So U plus varies as Y plus. And there is a overlap layer where the velocity profile is logarithmic. Now, this experimental data obtained by Lindgren also shows the same thing. Viscous sublayer with linear velocity variation and overlap region with logarithmic velocity profile. And in this case, it can be noticed that the outer layer, in the case of a pipe flow, also seems to show an almost universal structure in addition to the viscous sublayer and overlap region. The outer layer also actually seems to show a universal structure because all the data points from different Reynolds numbers seem to collapse onto the same curve. Uh, for the external flow, we mentioned that there was no universality in the outer region. Each one seems to follow a different curve, whereas in this case, all the data, even in the outer region, seems to collapse onto a single curve. So that's quite interesting to see that there is a universal structure exists not only in the sublayer and the logarithmic overlap region, but also in the outer region in the case of pipe flow. So what this establishes is that in the case of external and internal flows, there is a universal structure in the viscous sublayer with U plus equal to Y plus, and there is a universal structure in the inner layer with U plus varying as log of Y plus in both external as well as internal flows. Now, notice that the overlap region generally extends from Y plus of about 350, 35 to 350, and the viscous sublayer usually extends for Y plus about less than 10 or so. So the region in between these two, for values of Y plus between 5 and 35, is called the buffer region, and U plus in this case transitions smoothly from a linear profile to the logarithmic profile as can be seen here. So it transitions smoothly from the linear profile to the logarithmic profile. So this region is called the buffer region, that is Y plus between 5 and 35. And Spalding in 1967 derived a single velocity, a single expression for U plus that can be used all the way from the wall where Y plus is 0 up to 350. Which is the outer edge of the overlap region. So you can see that the expression looks like this. So and it can also be seen that this fits the experimental data extremely well all the way from Y plus of 0 through the buffer region to the outer edge of the logarithmic overlap region. So it can be seen that this works extremely well. And that is actually the expression that is widely used these days. And in fact, this expression holds up 350, and this is usually referred to as the law of the war. So in summary, we can say that the experimental data plotted in the previous figures for both external as well as internal flows, that is boundary layer flow in boundary layer over flat plate under different pressure gradients than external flow, and boundary layer in side pipes under a different Reynolds number, exhibit universal structure in the log-law region, which is the overlap region, and the sublayer, which is the viscous region, and they are applicable for any Reynolds number in both internal as well as external flows. Hence, we may use this with confidence for engineering calculations. Okay, so once we know these profiles to be universal and we know the exact analytical nature of the profiles, these can be very effectively used for carrying out engineering calculations in order to calculate both skin friction in external flows as well as pressure drop in turbulent pipe flows. This is what we will take up next.